welcome to I think it's the last session of the conference. This is a session on garbled circuits. The first paper is omega of 1 over lambda rate Boolean garbling scheme from generic groups by Geoffroy Couteau, Karmit Hazai, Aditya Hedge, and Naman Kumar. And Naman is giving the talk. Go ahead.
Yeah, thanks for the introduction. Hello, everyone. I'm Aditya, and I'll be presenting omega of 1 over lambda rate Boolean garbling from generic groups. This joint work with Geoffroy, Karmit, and Naman. So, okay, let's get started. So I get to introduce garbled circuits for the first time in this session. A garbling scheme allows a garbler to take a Boolean circuit and encode it and compute an encoding of the circuit called a garbled circuit and a key. Later, the key can be used to compute an encoding of the input. The evaluator can then evaluate the garbled circuit on the encoded input. Correctness states that the output of this evaluation is equal to the Boolean circuit evaluated on the original input. And the key property is the privacy property, which states that the evaluator who receives the garbled circuit and the encoded input learns nothing beyond the circuit output. In most applications, we will actually need to communicate this garbled circuit, which means that the size of the garbled circuit often becomes an efficiency bottleneck. And this is why a long line of research has focused on improving the size of the garbled circuit. And in fact, in our setting, the circuit is public, which means that the size of the garbled circuit can actually be much smaller than the size of the circuit. And we'll be using rate as a measure of efficiency. And rate is nothing but the ratio of the number of gates in the circuit to the size of the garbled circuit in bits. And what we want is higher rate garbling schemes, because this means the size of the garbled circuit is smaller. Okay, so taking a look at existing garbling schemes, on the one end, we have schemes from symmetry key crypto, which require of lambda bits per gate. And these schemes are actually black box in crypto. What that means is they make only Oracle access to some underlying cryptographic primitives. They can be implemented with only Oracle access to the underlying cryptographic primitives. And this is a very nice property to have, because this not only means simpler and more efficient constructions, any improvements to the underlying primitives immediately translates to the garbling scheme. On the other end, we have succinct garbling schemes, where the size of the garbled circuit is much smaller or independent of the size of the Boolean circuit. And these schemes are non-black box. For example, some of the schemes use ABE, where the ciphertext policy performs FHE evaluation. More recently, Liu, Wang, Yang, and Yu, they propose a rate 1 garbling scheme from the ring LWE and N-true assumptions. But even this makes non-black box use of a PRF. So the key question we ask in this work is if we can do better than rate 1 over lambda, if we can get an omega of 1 over lambda rate garbling scheme while being only black box in crypto. And we show that this is actually possible. We construct a garbling scheme in the generic group model, which requires lambda over square root log lambda bits per gate. We also have a construction in the standard model. So assuming par DTH and a tweakable correlation robust hash function, we show a garbling scheme for layered circuits that has similar efficiency as the GGM one, but has an additional circuit depth dependent overhead. So both these schemes have omega of 1 over lambda rate and make only black box use of crypto. And these are also one of the first schemes that achieve, that require sending fewer than lambda bits per gate, while from assumptions that do not imply FHE or that are not known to imply FHE. Okay, so for the rest of the talk, I'll be focusing on our first construction. So it turns out almost all garbling schemes follow a common template where the garbler and evaluator perform a secret shared evaluation of the circuit. And it'll be helpful to view the garbling scheme as a protocol where only the garbler sends messages to the evaluator. So what does this look like? So the input encodings given to the evaluator corresponds to additive shares of the inputs. The garbler and evaluator then perform a gate-by-gate evaluation to maintain the invariant. In particular, the garbling algorithm computes shares of intermediate values for the garbler and some garbling material, which the evaluator can then use to maintain the invariant on their side. Okay, so the problem of garbling now reduces to maintaining this invariant. And most garbling schemes, especially for maintaining the invariant for AND gates, require what I'm going to call as a multiplication gadget. So the garbler provides an input X, the evaluator provides an input Y, and what we want is to compute shares of X times Y. And we want to realize this gadget with a single message communicated from the garbler to the evaluator so that this message can then later be appended to the garbled circuit. But we can't realize this gadget with just a single message. What we need is the parties to also hold some correlated inputs. And the correlation we want is that they have shares of delta times the evaluator's input Y, where delta is some common public value known to the garbler. Sorry, no, it's not public. It's a private value known to the garbler, and delta is common across all invocations of the gadget. And when we use this gadget for garbling, the evaluator's input Y will actually correspond to its shares of the secret of the intermediate value. So what we'll do is actually change the invariant so that the garbler has a key, the evaluator has a label that corresponds to shares of delta times the evaluator's share of the intermediate value. And turns out this gadget actually suffices for garbling. So using such a gadget, we only need to make a constant in number of invocations of this gadget to construct a garbling scheme. Okay, so the focus then is on efficiently constructing this gadget. Yao's garbling scheme instantiates such a gadget, which requires O of lambda bits of communication from the garbler to the evaluator, which in turn leads to O of 1 over lambda rate. And to get better rate, we essentially need to send fewer than lambda bits for each invocation of this gadget. And to do this, we turn towards recent advances in arithmetic garbling. So recently, a recent work in Eurocure by the same set of authors as this work, we propose a multiplication gadget, a similar multiplication gadget over the integers, where the garbler and evaluator now input integers X and Y, and we compute shares of the output. So in particular, the correlated inputs correspond to shares of delta times Y over some large integer ring, and the outputs are shares of the product over the integers. In fact, we have a more general gadget which allows transforming the evaluator's input by some efficiently computable function f before multiplying it with the garbler's input. And our first observation is that this gadget is actually black box in crypto, and it can be proved secure in the GGM. And the gadget itself requires lambda bits of communication from the garbler to the evaluator. So now when garbling, in the case of arithmetic garbling, which is where this gadget was originally introduced, this requires, that ends up requiring lambda bits of communication. And since the gadget can be used for log lambda bit integers, this leads to a rate of log lambda by lambda, which is better than the baseline. But for Boolean garbling, we're computing over Z2, which means that the rate ends up being 1 over lambda, which is no better than Yao. So how do we get better rate? And this is the key component of our solution. We construct a packing scheme that takes bits of T bits and packs it into a log lambda bit integer. And the idea is that we can use a single invocation of the gadget to compute T gates in parallel and amortize the cost. But turns out we require some special properties from the packing scheme, which standard approaches to packing don't support. And one of our main technical contributions is coming up with such a packing scheme. So for the rest of this talk, I will primarily focus on the properties we need for the packing scheme by going over the template for garbling. Okay, so at a high level, what we want to do is, given T gates, we want to pack the right input wires, we want to pack the left input wires, we want to evaluate the gate over the packed values, and then unpack the output to get the values on the output wires. And of course, we want to do this in a distributed manner where to realize a garbling scheme. In particular, what we want is, given that some invariant holds on the inputs, we want to maintain the invariant on the outputs. And what is the invariant? The parties have Boolean shares of each input. and shares of delta times the evaluator's share over the large integer ring ZP. And we want the keys and labels to be over the large integer ring because we want to finally use it with the multiplication gadget. And once again, the high-level idea is that we can, if we can use compute over this packed encoding later on, we can amortize the cost of invoking the gadget and use lambda bits for evaluating over T gates. Okay. So the first step is that the parties simply pack their shares locally to compute packed encodings GR and ER. But notice that we want these encodings GR and ER to correspond to shares of the packed inputs VR. So this means that the packing scheme must be F2 linear. So this is the first property we want from the packing scheme. And then looking ahead, we will also want that the invariant actually holds over packed values so that we can use the multiplication gadget later to evaluate the gate. This means that we want shares of delta times the evaluator's packed share ER. And the question is, how do we compute this? And we can't just use the packing scheme directly because the labels and keys are shares over ZP. So what we're going to do is use the multiplication gadget. So the evaluator performs like a bit recomposition of its shares over the integers to compute some value E star. And then the garbler and evaluator aggregate their keys and labels over the integers. And then they use the transform and multiply gadget, which we saw before, where the garbler inputs delta and the evaluator inputs E star. And because E star was computed over the integers, they do have shares of delta times E star. This means that we can actually use the gadget. And the function that we're going to compute on the evaluator's input is going to be first doing a bit decomposition of the evaluator's input and then packing it. So what does this mean? The parties end up getting shares of delta times f of E star. This is just by definition of the gadget. And f of E star is actually nothing but ER, just by how the evaluator computes ER. So in summary, the parties so to do the packing, the parties just locally pack their shares of the wire values and use the gadget to compute shares of the packed keys and labels. And of course, the same thing works if you want to pack the wires on the left input wires. Okay, so next we want to evaluate the gate over the packed values, over shares of the packed values. And writing it out with a little bit of algebra, what we find is actually if you just compute these 4 cross terms, if the parties can compute these 4 cross terms, then we can actually compute shares of the product. And notice that we're actually hoping to compute over packed values with the aim of computing over the underlying tuples of bits. This means that the encoding must be homomorphic. It should allow computing this sum of product. So this is the second property we need from the packing scheme. And now going back to actually computing this, the first and the last term are available to one of the parties completely, so they can compute it locally. And we'll use the multiplication gadget to compute the other 2 terms. And this is fairly straightforward because, for example, if you take the second term, the garbler has G sub L, and the evaluator has E sub R, and the parties have shares of delta times ER. This is what we computed in the first step. So we can invoke the multiplication gadget and compute shares of this product. Good. So at the end of this, parties have shares of the packed output. And once again, we will want to maintain the invariant and compute shares of delta times the evaluator's share of the packed output. This is a little bit more technically involved, but it's not too hard with the multiplication gadget. So this can be computed, and you'll have to trust me for now. Okay. So finally, we want to unpack the shares and compute, maintain the invariant for the individual output bits. So once again, the parties are going to simply unpack their individual shares and obtain shares of each output value. Once again, this requires that the unpacking algorithm is F2 linear, and this is the third property we want from the packing scheme. But to maintain the invariant, we also want keys and labels of the output values. And we need to now convert our keys and labels over the packed values to individual bits. And of course, we can't just use unpack directly because there is a mismatch in the space over which these things live. So once again, we'll use the multiplication gadget. So the garbler inputs delta, the evaluator inputs its packed share E, and they already have shares of delta times E from the previous step. And the function they're going to evaluate is first do an unpacking of the evaluator's input and then output the ith bit. So this means that they get shares of delta times fi of e, and fi of e is nothing but the unpacking of e and the ith output. So it's nothing but the ith output share of the evaluator. But now to compute the t shares, we need to unpack for all the each of the gates. So we have to invoke the gadget t times. This means that the communication is actually t times lambda, which means that we end up communicating lambda bits per gate. And what we observe actually is that to actually improve the rate, the skills are rate. So to actually improve our rate, what we observe is that since the inputs are the same across all invocations, we can reuse the Gabler's message while computing over different functions. So we only need a single lambda bit or O of lambda bit message to unpack all output values. So at the end of this, what we have is parties just locally unpack their shares, and they also maintain the invariant for the output values. And this ends the complete evaluation of T parallel gates. Okay. So overall, the Gabler has communicated O of lambda bits because we've just invoked the gadget a constant number of times. This means that we've used O of lambda bits for evaluating T gates. So the total rate is T over lambda. And we'll be setting T to square root log lambda, which implies a rate of square root log lambda by lambda. But I want to spend like a few minutes on why we set the rate to square root, why we set T to square root log lambda. Well, the first reason is because our transform and multiply gadget, the evaluator's input has to be a log lambda bit integer, which means we can pack only log lambda bits. So T is at most log lambda. And we incur an additional loss because the multiplication gadget adds some noise to ensure privacy. And we need to compute homomorphically over the output of the gadget. And this requires packing fewer bits so that we can actually do homomorphic computation. So this sort of trade-off between privacy and homomorphism ends up in a quadratic loss, and we get square root log lambda. So in the time that I have left, I will briefly go over the packing scheme. So from our previous discussion, what we've narrowed down is that the packing scheme needs to have three properties, or the pack and unpack are F2 linear, and it should compute homomorphically computing sums of products. And we do this packing in two steps. First, we take tuples of bits and embed it into an extension field of F2. And then we embed the extension field of F2. It gives us enough algebraic structure to embed it into the integers. For the first step, we use reverse multiplication-friendly embeddings, which were introduced by Cascudo, Kramer, Jing, and Yuan in 2018. And RMFE embeddings actually satisfy all the properties we want. The pack and unpacking are F2 linear. They're homomorphic for sums of products. And actually, they are also compact. So the degree of the extension field is linear in the number of bits we are packing. For the second step, we just simply take the polynomial over F2, we lift it to the integers, and we evaluate it at a point n. And for the inverse operation, we take the integer, perform an n-ary decomposition of the integer, take each digit, and then view it as a coefficients of a polynomial over F2. So we'll just reduce it more to. And turns out, again, this is F2 linear, and we show that this actually provides some limited homomorphism. You can evaluate sums of k products as long as the point at which you're evaluating n is greater than k times m, where m is the degree of the extension field. Okay, so to conclude, we propose a square root log lambda over lambda rate garbling scheme in the generic group model, which only makes black box use of crypto. Concurrent work in crypto this year in this conference, Meyer, Orlandi, Roy, Scholl, and Eshai Lee Len propose rate 1 Boolean garbling from group-based assumptions. But these schemes too are actually non-black box in crypto in the sense that they require non-black box use of a PRF. So a very natural open question is if we can get better rate while continuing to be black box in crypto. And I think it's also interesting to see if we can do better than Yao's garbling from a different set of assumptions, either from groups or lattices, basically diversify the set of assumptions. And with that, I'd like to conclude. Thank you.
Okay, we have a couple of minutes for questions. While people are thinking, I want to ask, have any idea for how fast you can compute those gates?
So I
to
don't
generate
think it is going to be efficient, concretely efficient. So I guess it's a scale. Like compared to the schemes here, I think I would be more happy to implement this.
Yes, sure.
Yeah, but I don't think it's going to be as efficient as this. Definitely, maybe comparable to this.
So
Yeah.
ballpark, couple hundred gates per second, couple of thousand gates per
I
second.
don't know a concrete number off the top of my head, but I guess the inefficiency is that we need to do a lot of group operations for each gate, which I'm guessing is going to be quite slow. So
For each packed gate.
yeah, we need to do like poly lambda, like proportional to the number of, like 2 to the number of bits we are packing. So.
Okay. All right. Question. Okay, go ahead.
Yeah, just want to clarify. It seems that you are like kind of packing like square root log lambda gates in parallel. So does that mean like the RAID only works for certain types of circuits? If like it's super sequential, does it still work?
So the only thing we require is that the circuits are wide enough to have square root log lambda, so that if it's very narrow and very long, actually even that it would work. Sorry, you only require square root log lambda depths. These packings are not really affected by if they're at the same depth or not. So I think all you require is it's. Yeah.
I see.
So it can be on different depths.
I think so. Yes. Our par DDH based scheme has a depth based dependency, like the one in the standard.
One wire can depend on the wire that is computed in the same gadget.
Yes, because it's a garbling scheme. I think that's not right.
Okay, all right. Let's thank the speaker again. Okay, the next talk is re-randomizable garbling revisited. Speakers are coming up. Okay, well, they're setting up. It's re-randomizable garbling revisited by Raphael Johan, Jonas von der Heijden, and Tibor Jager. And Raphael and Jonas will give a talk. Go ahead.
Okay, so I'm Jonas. This is my co-author Raphael. I'm presenting joint work with Tibor Jager on re-randomizable garbling. So the setting we're looking at is outsourced multi-party computation. So we have a large number of resource-constrained clients, a small committee of high-performance servers. And the goal is that the clients can outsource the heavy lifting of MPC to the servers without losing privacy and without having to trust the servers. So in the top row, we have the clients. In the bottom row, we have the servers. And the clients send their inputs to the servers in some encoded form. And then the servers compute, and eventually they will reply with the function output, potentially also in some encoded form. Now, the problem that we could face is that we have an adversary who notices that who the committee is, and because the committee is so much smaller than the number of clients, it will be almost certainly below the corruption threshold of the adversary. So the adversary could just corrupt all the servers, the whole committee, and if the computation between the servers has some kind of assumptions about dishonest majority or honest majority, then we have a problem. What we need is outsourced MPC with semi-honest security against adaptive server corruptions. So here's this is the state of the art, and so at least for constant round protocols. So on the one side we have FHE-based schemes like the scheme from Moshe et al. On the other side we have garbling-based schemes. So for example, scales. And the problem we face with scales is that actually evaluating an AES circuit, just the server cost is in the order of years. And we're going to improve this by 4 orders of magnitude. So the construction of outsourced MPC via garbling, at least in scales, looks like this. So we're using re-randomizable garbling schemes, and re-randomizable garbling schemes we have work like this. So we have the first server garbles the circuit, and then the next servers in the row are re-randomizing the garbling. And now in scales, we also have the clients, and the clients are exchanging using oblivious transfer. They're exchanging their inputs against input labels, or for the re-randomized circuits, they're getting transformation functions from the servers. And so the security guarantee of re-randomizable garbling is that as long as one of the servers in the chain is honest, we still have garbling privacy of the last server in the chain. So then once the clients have exchanged the input labels and the transformation functions with the servers, they can reconstruct the input label of the last garbled circuit and then evaluate the circuit. So what do we need for RGS? RGS require key and message homomorphic encryption. So we have scales, which is outsourced MPC. This is based on re-randomizable garbling. And re-randomizable garbling is based on KMHE. The only known KMHE so far that meets all the requirements we need for RGS is BHHO, which was invented 17 years ago for primarily circular security. And one ciphertext in BHHO has size on the order of kappa squared. And to create the ciphertext, to create an encryption, we require kappa cubed exponentiations. And this is a problem because for typical security parameters like 128, kappa is actually around 520 or 560. So this is very inefficient. So our goal in this work is to improve the KMHE efficiency, to in turn improve RGS efficiency. And we actually do this. So we construct much more efficient KMHE. And we devise new KMHE and RGS definitions that address some gaps in scales and allow for the use of our KMHE. And we also introduce a new gate KMHE primitive, allowing for randomness reuse across garbling table ciphertexts. And we computed some performance estimates for our RGS. And here we assume that we instantiate scales, which is BHHO based, with curve 25119, and our work, which is pairing based with curve BLS 12381. And then based on this assumptions, our performance estimates is that we can reduce the size of a garbled gate by 2 orders of magnitude, so from 133 megabytes to 1.35 megabytes. That we can improve the efficiency of garbling a gate by 4 orders of magnitudes, from 33 minutes to 40 milliseconds, and then that we can even improve the re-randomization performance by 5 orders of magnitudes, from 2.23 hours to 50 milliseconds. And that's it from my side, and I hand over to Raphael.
Yeah, thank you. So I'm now going to talk about our new key and message homomorphic encryption scheme and how it improves upon the previous variant. So to do that, I will intuitively describe the requirements we need for the KMHE scheme. So, you know, a key and message homomorphic encryption scheme is basically an encryption scheme where you have a homomorphism in the keys and also a homomorphism in the message. And we will consider a secret key scheme here, so secret key encryption, because that is what you need for Boolean circuit garbling, or the standard versions of that. So the requirements are intuitively described roughly that we will need the same homomorphism in the key and the message space. This is because for garbled circuits, you encrypt the wire labels and you also use those wire labels as keys. And we want to be able to re-randomize those wire labels consistently. So we need to be able to apply the same homomorphism to the wire label in the key and also the wire label in the message space. This is not so easy to find schemes that do this. For example, if you consider El-Jamal, then clearly it has an additive homomorphism in the key. But for example, if you try to do an additive homomorphism in the message space by encoding the message as G to the M, then you would need a discrete logarithm to decrypt. Now there's another requirement which we call key privacy under leakage in our work, but in the previous work by Karia et al. Has been called KMH privacy. And this requirement basically says that if I give you a key and the re-randomized key sigma of k, then this should not leak the function sigma that you apply to it. And this is very restrictive already on the homomorphisms that could work here. For example, if you use addition over the rings of integers modulo p, then if I give you a key, which is an integer, and the transformed key k plus sigma, then you can immediately compute the function sigma from this, just via subtraction. And of course, the last requirement is that we need to be able to re-randomize the ciphertexts completely. So this is in terms of the encryption randomness. So with that and the homomorphism, we can basically encrypt, re-randomize every part of the ciphertext. Okay, so now I want to go into roughly a simplified version of the encryption algorithm of our KMHE scheme. So the main part that will improve the efficiency is the use of pairings. So we have a set of algorithms which again sets up a bilinear group. So we have two source groups, which we denote by G and H. And we have a group order, which is Q, and we have a target group GT, and we also have some generators for those groups, plus the pairing E. And then since we have a secret key scheme, we will need some kind of key generation algorithm. And there we sample random kappa length bit strings with the additional requirement that the Hamming rate of these must be exactly kappa half. This means that half of the bits will be zeros and half of the bits will be ones. And now let's look at the encryption algorithm. So you can think of this as a version of El-Jamal, where the key is a bit string, and we also, of course, want messages to be bit strings because we want to be able to encrypt keys. So if you look at the Y value, then you can think of this as a form of El-Jamal public key, but in the target group. Now to recover in El-Jamal, you actually have a G to the X, but to recover this G to the X from a bit string, we have this product of GI to the KIs. And as long as these KIs have sufficient min entropy, you can just use a leftover hash lemma argument to argue that this product looks like a G to the X, which is random. And then you basically have a El-Jamal public key, but in the target group. And then to encrypt a message, we use like the previous works, we use a bitwise encryption. So we take each message bit and encrypt this just using El-Jamal now in the target group. And then the ciphertext will be just the ciphertext and the basis elements plus the public key which we need for re-randomization. Okay, so why does this fulfill the requirements we set on the KMHE? So the important part is here that this scheme allows for a bit permutation homomorphism. So why is a bit permutation homomorphism the right choice? Well, if I give you a key with Hamming weight kappa half and I give you the permuted version of this, then this will tell you very little about the permutation that was applied. Because if you think about the output of the permutation, for example, a 0 bit, then there are many 0 bits in the input that could have been mapped to this output 0 bits. So you don't really know which of the input 0 bits were mapped to this output 0 bit. So how does the scheme achieve these homomorphisms? Well, it's not so complicated, since each of these group elements G1 to G kappa is tied to a key bit. You can just permute the key bits, these group elements, and with that transitively also permute these key bits. And then for the message bit permutation, since we encrypt each message bit separately, we can just permute these ciphertext elements. And then we have the same homomorphism in the message and the keys. And now the last part is re-randomization, and this is fairly straightforward based on DDH, or a generalized variant of DDH. So why does this scheme kind of do so much better than before? Well, the BHHO-based scheme from AHKP22 and GHV10 needed to store every combination of these bases G1 to J kappa and A1 to A kappa. And this is kappa squared many. And using this technique of pairings, we can supply the GIs and the H to the AJs separately and then combine them during decryption on the fly to get these quadratic many combinations, but using only a linear amount of space. Okay. So that's kind of the idea of the KMHE scheme. But of course, for garbling, at least for Boolean circuit garbling, it's not enough to have a scheme where you have a single secret key. So you want generally a scheme where you have 2 secret keys, because each gate gets 2 input wires. So we'll have 2, and then depending on the value of these input wires, you will want to decrypt the right ciphertext in this garbled table. Now there are some different ways to get such a double key scheme. For example, in the original work of Scales, they used a secret sharing approach where you just share the message among 2 ciphertexts, and then each ciphertext can be decrypted with one of the keys, and then overall you can decrypt both. If you have both keys, you can decrypt both ciphertexts and then recover the message. Now, since our goal was to get the best performance gain possible, we devised what we call gate KMHE, which encrypts the entire garbled table in a single operation. So the whole garbled table you see there is created by a single call to this encryption primitive. And this halves the ciphertext size compared to using a secret sharing approach. So this is quite a big performance gain again. And we also, using this new primitive, necessitated creating new definitions for it, and also proving the construction of re-randomizable garbling secure from those new definitions. So to conclude, re-randomizable garbling and the outsourced MPC based on that allows for adaptively secure, since it's basically in the YOSO model, outsourced and constant round multi-party computation in the setting of a dishonest majority, while relying only on the simple assumption of a public ledger. And we devised the pairing-based KMHE, which improves the ciphertext size significantly by 2 orders of magnitude, the runtime by 4 to 5 orders of magnitude, and then also devised this gate KMHE primitive to further improve the performance. And lastly, we on the way we changed some of the original RGS definitions in the original work by Akaria, Hazai, Kolesnikov, and Prabhakaran. But so they have also fixed these gaps, but in a slightly different way, which was not compatible with our scheme. Yeah, since they basically have a scheme that's perfectly re-randomizable, and this is not, our scheme is not perfectly re-randomizable. So to finish, I will link you to our paper, and I think Jonas also has something he wants to say. I will just click forward.
Yeah, you can hire me. So I will defend my PhD thesis in October. I'm looking for a position in research or at the intersection of industry and research or engineering and research anywhere on Earth.
Thanks for listening.
Okay, we have a couple of minutes for questions. Yeah.
The original motivation of BHHO of just circular security, does this give any advantage?
You mean
If we're just going to use this instead of BHHO in order to get circular security, is it better than BHHO?
We don't have
circular security. That's the main.
Why?
Because you don't have enough group elements, I think, and you don't have enough degrees of freedom in these group elements to program the secret keys. So we tried it to try to look at it, and it seems to be not circular secure anymore. So it's kind of what you lose.
It's key leakage resilient though. So anything that uses BHHO for key leakage resilience, you can use our scheme for also.
More questions? Okay, let's thank the speakers again. Okay, so the next paper is silent circuit relinearization, sublinear size, Boolean and arithmetic garbled circuits from DCR by Pierre Meyer, Claudio Orlandi, Lance Roy, and Peter Scholl. And Lance is going to give a talk.
Thanks for the introduction. So today I'm actually going to start out a little bit talking about some basically advanced cryptographic primitives are really just constrained PRFs from HSS as sort of a warm-up for building garbling. So I'll talk about that, a new technique for homomorphic secret sharing we introduce, and how to apply it to garbling. So there's a long line of work on distributed discrete log technique that was introduced by the seminal work of Boyle et al. In 2016. The distributed discrete log technique allows for homomorphic secret sharing where you have something where you have like encryptions and you have shares and you can multiply encryptions by shares to get more shares. This is like being able to do some sort of product is quite non-interactively is quite powerful. And it's useful to get two-party computation with a log factor saving in communication. However, it's like secret sharing style two-party computation, so the round complexity grows with the number for the depth of the circuit. So I'll get back to that later. In terms of directions most relevant to this talk, there's the work of CMPR in 23 that showed how to make one-party share, let's say Alice's, one party's output share independent of the input to the computation or some of the inputs. So this is what's needed to build a constrained PRF. And then we improved this technique in TCC 24 and showed how to get rate 1 garbled circuits, arithmetic garbled circuits. And a further follow-up is we show how to do privately punctuable PRFs. Now, in today's talk, I'm going to be discussing this technique and consequences of a technique which lets you actually multiply shares directly. So here they're multiplying share by encryption. All of these require encryption. These we're multiplying authenticated shares directly with each other. using some sort of like an encrypted gadget, I guess. The main limiting factor here is that these X and Y will have to be known by the same party. Now, what this is useful for is you can do sublinear communication. I'll show you how to do sublinear garbling, communication garbled circuits. But first, I'll have to talk about constrained PRFs. Okay, so there's a I should mention, of course, there's the parallel work of that you heard about on Wednesday of Shai Li, and then I'll also show how to do this construction. Okay, so then next I'll talk about here's some history of garbled circuits and attempts to make it more succinct. It was first made like succinct in terms of comparison to the circuit size, using either obfuscation or like techniques from lattices. In terms of like group-based techniques, it's quite a bit more difficult. The ball got rolling with like a work of Ball et al. In 23. Showed how to do constant rate arithmetic garbling from linear homomorphic encryption. And there's been a lot of follow-up works improving on this, doing this from like HSS techniques and different assumptions, and including the present work and the concurrent work of Ishai et al. I should also mention the work of Liu, Wang, Yang, and Yu, who do something based on, they have a construction based on like lattices that is, I think, a similar kind of techniques to what you can do with the techniques I'm talking about here. So first, I'll be talking about doing constrained PRFs. So constrained PRF, Alice is able to generate some key K and use it to evaluate a PRF on some arbitrary input X. So a K defines some function. And the problem we want is that we want Alice to be able to give Bob the ability to evaluate the same function, but only when the description of the constraint allows it. So when the constraint description says 0, it's allowed to decrypt, allowed to be evaluated, then Alice and Bob should get the same result. Otherwise, they should get Bob should get something independently random. If you look at this as like a secret sharing thing, they get shares of 0 if the circuit values to 0, saying it's allowed to decrypt. Otherwise, they get shares of something random. Now, with this sharing perspective in mind, turns out there's a connection to like HSS, or you can use HSS for this. So if we have some way to build to authenticate the computation of this constraint function, then we end up with like shares of 0 if the constraint function is 0, or shares of this value delta. Delta is the HSS secret key if the constraint is 1. So the point is that when the constraint values to 1, Bob cannot predict Alice's key result. And so just hashing the result would then be sufficient to build a constrained PRF. So if you want to build something like this, what we need to do is have some way of like authenticating some arbitrary computation on some input C in a way that is, that allows Alice to compute or share without knowing C before C is chosen. Those are the requirements. Because for constrained PRF, Alice's like the master key has to be something you can evaluate before you know the constraint. Alice's share has to be independent of like the description of the constraint. However, we're just talking about constrained PRFs, not private constrained PRFs. So one thing that makes things easier is that Bob knows the description of the constraint. So what do standard HSS techniques give us? So you look at the HSS instruction for Damgard-Dirac of Roy and Singh, then you have something with like a group where you have a subgroup where discrete log is easy, where you can code messages. So this group will be ciphertext. You have a subgroup where discrete log is easy, you can code messages. You have another subgroup that's like used to hide the messages, where discrete log is hard. And so there's two main like useful things here. One is that we have this efficient discrete log computation you can do in the subgroup where discrete log is easy. And more importantly, we have this distributed discrete log computation. So if you done a decryption in secret shared form, meaning you have multiplicative shares of something in the easy discrete log subgroup, then you can use, just do local computation to get additive shares of the discrete log. So then this is used to build like homomorphic secret sharing by, if I have some shares of, okay, so if I maintain an invariant that like the calculations I'm doing are the form I have some secret key delta multiplied by a value of every like wire in some like calculation. I can do additions just by addition because it's additive shares. If I want to do multiplication, it's a bit trickier, but we can use the discrete log to help us out. The point is that if the shares of inputs are multiplied by a secret that matches the decryption key, same as the decryption key of encryption of the other input, then we put in the exponent, it decrypts automatically for you to get multiplicative shares of the decryption, and you can take a discrete log to get additive shares of the decryption. So what this means is that if we have secret shares of the secret key delta times x, some x, and we have an encryption of y, then we can non-interactively compute secret shares of the secret key times x times y. Now, unfortunately, this isn't sufficient for the problem because, well, two things. One is that the multiplication is only by inputs, so we can't do an arbitrary computation. We can only do like a RMS program or like something similar to like a branching program. Also, this process depends on having encryption of the inputs, which means Alice's evaluation will depend on the constraint, so that's not okay. So our technique to get around this problem is what we call silent relinearization. Silent relinearization. So we're inspired by the Quicksilver zero knowledge proof system, where it's a vol-based zero knowledge proof. Where so imagine like Alice is a verifier and Bob is a prover. Alice has her some key delta, and we want to do some like check on multiplications. In Quicksilver, what you do is you just have Alice multiply her authenticator values locally, and you can then see what happens on Bob's side. You write Alice's shares in terms of Bob's, and is like a polynomial in the secret delta. Expand. You find there's one term here that corresponds to like the authentication or result, plus some cross terms that we aren't super interested. Now, if you rearrange this computation, we find that like having the parties just multiply their authenticator values locally will give us a multiple of the secret delta, which is useful. You saw before with the homomorphic secret sharing thing, being a multiple of the secret delta is what allows a multiplication to occur. So this RSC seems somewhat promising. If we can get rid of this delta though, then we find we have authentication of the value we want, plus some cross terms that we need to get rid of. So, okay, imagine that, yeah, so if we make a key to depend message assumption, security assumption, then we can encrypt the multiplicative inverse of the key and use that to go from shares of delta times this value here to just shares of this. So we can get rid of the delta. So you get shares of this thing. Then finally, if you notice, these are all values known to Bob. These are like plain text values and Bob's shares. So Bob can locally remove them from his share of the authenticator. So they get authenticated shares of alpha beta. They get shares of delta alpha beta. And that's exactly the same format as what is needed for the input of this. So that means that you can go through sort of an arbitrary arithmetic circuit, do additions, multiplications, and get, as long as Bob knows all the values that are being computed on, then at the end you'll get authentication of the result in the form of share of delta times the result. So to summarize this process of multiplication, Alice and Bob have authenticated shares of alpha and beta, and Bob has alpha and beta, then they can, if they locally multiply their shares, they get a secret shares of like delta times this thing, authenticator, this blue term. They can remove the delta of a distributed discrete log in this like helper ciphertext to get, and then finally Bob can remove the cross terms by just a local computation, and they get products of, they get the authenticated share of the product. So what can we do with this? So we use this to build something we call semi-private offline-online homomorphic secret sharing. So it comes in sort of, yeah, the computations we do are sort of described in two steps. So first is the part we just talked about. If I have authentications of some input X that Bob knows, then we can get authentication of the result of that computation. And additionally, we can do like classic HSS to, if we have some multiple encryption of some input Y, then we can compute an RMS program on Y and have that get multiplied into the existing share. So we can get secret shares of the secret delta times some public computation on Bob's input times some public computation on a private input. So the properties that, so there's two types of inputs. One is known to Bob and is online, meaning that because Alice's only depends on this input as a form of this share that she could sample ahead of time, Alice's computation is like information theoretically independent of X. Like it can be done before X is chosen. The other type of input is Y. It is private, but the downside is that it has to be chosen in advance because Alice's calculation does depend on it. All right, so how do we use this primitive for sublinear communication garbling? So our goal will be to not to directly do garbling of sublinear communication, but rather do linear communication garbling for for circuits of like a larger class. So you're going to be looking at truth table circuits where each gate is some arbitrary truth table, arbitrary public truth table that takes some log and the security parameter many inputs. And it's known from Couteau et al. That any circuit can be, any layered circuit can be compressed by a log-log factor when you represent it in this way. So then our goal will be to garble these with rate 1 using 1 bit per gate. And then we get something that has a log-log savings when you do the fan-in corresponding fan-in 2 circuits. So how the garbling scheme work, just like the usual like point per mute garbling schemes are going to have a mask for each wire that then allows each the evaluator to get like a color bit as like the masked version of the wire. So that way the evaluator has something public it can work on. It can work on with semi-private HSS on. Additionally, there's going to be an authenticator value that's the bulk of the wire label. The wire label itself is going to be the color bit that's published to the evaluator, and the authenticator wire label, its share of the authenticator. And then the masks will be chosen as the output of some PRF. That's important for like compactness. So so far that describes how the wires. Now the question is, if we have this information for the input to a gate, how do we get the output wire label for the gate? So the idea here is that from this the information we have here, this key that was used to generate the masks, and from the Bob's inputs here, we have enough information to unmask the input, evaluate the gate, and remask it again. So assuming the semi-private HSS is powerful enough to do this computation, we can get secret shares of the masked result of this gate. And additionally, we can get secret shares of the like delta times this authenticator value for it. Assuming that works, then we can just have Alice send her share to Bob. Bob will do Bob can then reconstruct the masked output, and then he has the 2 parts of his wire label for the output. And this can be shrunk down to just a single bit per gate if we're talking about Boolean garbling. because this masked value is just a single bit. So you only need this value mod 2 to reconstruct. So the final step I've left out here is just, is this actually something you can evaluate inside semi-private HSS? To see why it is, okay, the computation we're doing, the masked version is going to be that we unmask the input color bits, apply the gate, and remask the outputs. This can be written in sort of one hot garbling form, where we're summing over all possible masked inputs and calculate, okay, if the masked inputs were U1 to UL, what would the masked output be? And then selecting the correct value by multiplying by a vector that's 1 in the position corresponding to the actual masked input and 0 is elsewhere. Now, I notice the term on the left is something that depends on public information and these mask bits, which are all come from the PRF key. So they're all can be validated in HSS, assuming the PRF can be validated in HSS. So this can be like a classic HSS computation. And the values on the right are all public functions of Bob's inputs. So Bob's authenticated values. So this is the semi-private HSS computation. And recall we could do evaluate products. And of course, since this shares, we can evaluate the sum at the end. So therefore, this is something we can compute inside the semi-private HSS. So with that, I'll just leave you with a summary of our results and take questions.
We have some time for questions. So this is the focus here is the malicious model for lookup tables.
Semi-honest. So like both parties know the lookup table. So like I guess I'm not sure why it would make it.
Okay. And what sizes lookup tables you have in mind for this? Like, what's a good regime for your construction?
So we need the lookup table to be represented like with a polynomial amount of computation. If you're talking about concrete efficiency, I have no idea if this can be concrete efficient at all. But I expect that the concretely efficient setting would be small lookup tables and just trying to take advantage of like the bit complexity, like only needing 1 bit per gate, rather than trying to like blow things up and get a log-log factor.
Okay, thanks. More questions?
So the results summarized here are for general layered circuits. Sorry, I forgot to add that adjective here. So we first do garbling for lookup table circuits with linear communication. And then you can generically transform layered circuits into smaller lookup table circuits. So therefore, the smaller, if you shrink the circuit size, you also shrink the communication.
Can you comment a bit on the difference between your work and the Hanjun Lee's work on Wednesday? So like, I think both of you have like log saving and also like a semi-private part of the construction.
I think our techniques are very similar. The one main difference is that we only consider DCR. We did not try to do LWE or DDH constructions. I think they don't have a construction from plain DCR, which we do. Yeah, I think it's basically the same technique, just slightly different flavors.
Okay, let's think once again. Okay, we're now ready for the last talk of the conference. And we will know the title very soon. Okay, so the last talk is authenticated bit GC for actively secure RAID 1 to PC by Hanlin Liu, Xiao Wang, Ken Yan, and Yu Yu, and Hanlin is giving the talk.
Thank you for your introduction. Hello everyone, I'm Hanlin Liu from Northwestern University. Today I'm presenting our paper, Authenticated with GC for actively secure RAID 1 to PC. This is joint work with Xiao Wang, Kan Yang, and Yu Yu. First of all, let me review the background of the 2PC. Alice and Bob set the input to a functionality, then returns to the output fxy to both party. We want to decide a constant round crypto protocol to realize this functionality for activity security. Even if one party behaves arbitrarily, they can learn nothing beyond the output. For construction, used the Yao governing scheme, the communication target is at least lambda bits, but they are very efficient. For succinct construction, using the FHE or bootstrapping, they have a small communication, but the computational cost is very high. So, how to balance the communication and computation? Recently, some work focused on the middle ground in the semi-honest version. They have a small communication about the circle size plus poly lambda, and very fast computation without FHE or bootstrapping. Our work focuses on the middle ground in the malicious version. Here we show the motivation of our paper for succeed construction, which use the bootstrapping and the computational cost is very high. In our scheme, we only need a simple computation target without use the bootstrapping. For construction, use Yao governing scheme, they need a linear sized target communication, and we reduced to the 1-bit target. First, we recap the bit GC result. The computational is only constant number of homomorphic operation target without bootstrapping, and the communication is a 1-bit target. Our authenticated bit GC achieves the malicious security under the sum assumption with 2 times computational cost. Communication is also small, only 1-bit target and a constant round. In bit GC, the while labels are over polynomial. The first coefficient, global K delta, is equal to 1, and the permutational bit, pi a, is equal to the next significant bit of A0. And A1 is a sample A0 plus or minus delta, based on the value of the permutational bit. BitGC also introduced somewhat homomorphic encryption with a distributed decryption. The most important properties is a distributed evaluation. The first evaluate function used the label A pi A XOI and B pi B XOJ is written by the evaluator, and the next evaluator function used the label A pi A and B pi B is invoked by the garbler. The difference between the two labels, the difference between the two results has a formula as message times delta. Here we showed the high-level idea about the BitGC for governing one label, one gate. At the beginning, the garbler has 2 labels for each while, A1 and A0, and B1 and B0. And the evaluator has 1 label for each while, AVA and BVB. VA and VB are the input for this gate. Then, both parties homomorphically compute the encryption of the truth table, we call the TED tau. Then Gabler invoke the evaluate function over the TED tau and gets the permutational bit pi c from the next significand of this result. Next, the Gabler computes the d equal to random bit RC XOR permutational bit pi c and set the d to the evaluator. If the d equal to 1, then both party flip the ciphertext of the ciphertext in the truth table and get the ciphertext tau. Finally, both party invoke the evaluate function over the tau. Based on the oddness, the next significand of evaluate function over the TED tau is the same as the evaluate function over the tau. Then, whatever used the TED tau or tau, the permutational bit is the same based on the oddness. And based on distributed evaluation, the Gabler will get the two label C0 and C1 for the output well, and the evaluator will get the CVC, where VC is the output for this gate. Moreover, both party can get the ciphertext of the permutational bit pi c. The communication of the random bit RC is very cheap because we use the homomorphic PRG to extend the ciphertext of the seed. To achieve malicious security, we need to introduce a check to verify the single bit communication for each while. We observe that if the Gabler does not know the global key delta, then the encryption can be seen as the commitment. Then based on the authenticated framework, we can prove the BitGC is active security. First, we introduced a modified BitGC where the Gabler does not know the global key delta. In other words, the Gabler only knows the label AUA and BUB. The Gabler also can compute the permutational bit pi c because they know the UA and UB, only working as the evaluator. Used the proof of the original BitGC, we can show that the modified BitGC is also a gambling scheme. Finally, we showed the high-level idea of our authenticated BitGC for governing an AND gate. First, both party working as the modified BitGC, and then the evaluator set the ciphertext of the masked bit to the Gabler. We can reduce the communication of this step. Also use the homomorphic PRG used in the BitGC, only taking 1 bit per gate. Finally, both parties compute the ciphertext E over the encryption of the permutational bit and the masked bit, and check the E is the encryption of 0. We also showed that if the encryption E is ciphertext of 0, then both parties follow the protocol. We can further reduce the communication by this optimization. We can check a small cycle directly, not checking each gate. Thank you. That's all.
Okay, well, that's good. It allows us to go see the closing remarks in time. Do we have questions? Okay, there's no questions. Let's thank the speaker and all the speakers of the session and all the speakers of the conference and yourselves.